Jake Morrison pressed his face against the cold window of the transport ship and watched the Zephyrian Institute grow larger in front of him. The space station looked like a giant crystal flower floating in the darkness between stars. Its towers stretched out in all directions, each one glowing with soft blue light. Ships from dozens of different worlds moved around it like busy insects. His stomach felt tight with worry. 3 months ago, Jake had been a normal college student studying engineering at a small university in Ohio. Now he was about to enter the most famous school in the galaxy, surrounded by the smartest beings from 100 different planets. He was 19 years old and felt like a child about to play with giants. The transport docked with a soft bump. Jake grabbed his single bag and followed the other passengers through the airlock. The moment he stepped inside the station, he knew he was in trouble. The walls seemed to be made of living metal that shifted and changed color as he walked. The floor felt soft under his feet but made no sound. Even the air tasted different, clean and sharp like mountain wind. Other students moved through the halls around him. Jake saw beings he had only read about in books. A creature that looked like walking water flowed past him, leaving no trace on the floor. Something with too many arms and eyes that glowed like stars nodded at him as it passed. A being made of what looked like purple smoke drifted by overhead, paying no attention to gravity. Jake felt very human and very small. He found his way to the registration area, where a helpful computer voice guided him through the process. The machine scanned his DNA, recorded his voice, and took pictures of his eyes. It spoke to him in perfect English, though he could hear it talking to other students in languages that sounded like music or static or whale songs. His room assignment appeared on a small screen. Level 47, Section C, Room 891. Jake took the lift up, watching through the transparent walls as the station spread out below him. Gardens hung in the air without any visible support. Students sat in floating chairs, reading books that projected words directly into the air. A group of crystal beings played what looked like three-dimensional chess on a board made of pure light. Room 891 was small but comfortable. It had a bed, a desk, and a window that looked out at the stars. Jake set his bag down and sat on the bed, feeling the weight of what he had gotten himself into. He was the third human ever accepted to the Institute. The first two had graduated 50 years ago and become famous scientists. No pressure at all. His roommate arrived an hour later. Finn was from Altair 7, a world known for producing some of the galaxy's best mathematicians. He looked mostly human except for his pale blue skin and the fact that he had 2 hearts that beat in a rhythm Jake could hear when the room was quiet. Finn was friendly and spoke excellent English, though he sometimes used words that made Jake's head hurt just thinking about them. That evening, Jake attended his first class, Advanced Theoretical Applications with Professor Veltar. The classroom was huge, with seats arranged in a circle around a central platform. Students filled about half the seats, representing more species than Jake could count. He took a seat near the back and tried not to stare at his classmates. Professor Veltar entered through what Jake had thought was a solid wall. The professor was 10 feet tall and looked like a walking crystal sculpture. Light seemed to flow through their body like water, changing colors as they moved. When they spoke, their voice came from everywhere and nowhere at once, somehow speaking directly into Jake's mind rather than through his ears. "Welcome to Advanced Theoretical Applications," Professor Veltar said. "This course will challenge everything you think you know about science and engineering. You will learn to think beyond the limits of your species and your world. You will discover that the universe is far stranger and more wonderful than you ever imagined." The professor moved to the center of the room and waved one crystal in hand. The air above them filled with images, stars and planets, strange machines that defied explanation, cities that floated in space, creatures that lived in the hearts of suns. "Your final project will be worth 60% of your grade, Professor," Veltar continued. "It will test not just what you have learned, but how you think. The problem is real, and the solution you develop could be implemented in the galaxy's outer rim colonies." Jake felt his stomach drop. He looked around at his classmates who were all listening with calm attention. These beings had grown up with technology that seemed like magic to him. Their civilizations had been traveling between stars since before. Humans had invented writing, Professor Veltar gestured again, and a three-dimensional map appeared in the air above them. It showed an asteroid field with mining platforms scattered throughout it. Red lines connected the platforms, but many of the lines were broken or flickering. The Outer Rim mining colonies face a critical problem, the professor explained. They need stable energy distribution across multiple platforms in an asteroid field. The gravitational anomalies and electromagnetic interference make conventional power systems unreliable. Current solutions fail within months of installation. A student near the front raised what looked like a tentacle. Professor, what parameters should we consider for exotic matter solutions? All options are available to you, Professor Veltar replied. Quantum entanglement networks, dimensional phase shifting, temporal energy loops, consciousness, bridging, whatever your species has, developed or can imagine. Jake opened his notebook and wrote down the few terms he understood. Around him, other students were already discussing complex theories and advanced technologies. He heard mentions of quantum tunneling, reality anchors, and something called dimensional matrix engineering. You have 12 weeks to develop your solution, Professor Veltar announced. Present your designs at the end of the semester. Remember, the best solution is not necessarily the most complex one, but the one that solves the problem most effectively. As the class ended and students began to leave, Jake sat frozen in his seat. Everyone around him was talking excitedly about their ideas. He heard plans for machines that could bend space and time, networks that existed in multiple dimensions at once, and energy systems that drew power from the thoughts of living beings. Jake looked down at his notebook where he had managed to write only a few basic facts about the problem. He had brought a simple calculator and his old physics textbook from college. Compared to what he had just heard, his tools seemed like toys. Walking back to his room, Jake passed groups of students. Working together, their conversations filled with concepts that made his head spin. He felt like a caveman who had stumbled into a conference of rocket scientists. The worst part was that he genuinely wanted to succeed, but he had no idea how to even begin competing with minds that could think in dimensions he could not imagine. That night, lying in his bed and listening to Finn's double heartbeat, Jake stared out at the stars and wondered if coming here had been the biggest mistake of his life. 3 weeks into the semester, Jake felt like he was drowning in concepts he could barely pronounce, let alone understand. Every day brought new lectures about technologies that sounded more like fantasy than science. His classmates discussed quantum consciousness bridges as casually as Jake might talk about changing a light bulb dot in the library. Jake spent hours trying to make sense of textbooks written for minds far more advanced than his. The words swam on the pages: dimensional phase coherence, exotic matter manipulation, temporal energy cascades. He would read the same paragraph 10 times and still have no idea what it meant. Meanwhile, his classmates were already deep into their project designs. Zara, the gaseous being from the ethereal collective, had proposed linking the mining platforms through a network of consciousness-connected energy nodes. She explained to anyone who would listen that her species had long ago learned to share thoughts across vast distances, and energy could follow the same pathways as consciousness. Crix, a Vorthan with 4 arms and skin that looked like polished metal, was working on self-replicating quantum tunneling devices. His people had mastered the art of making machines that could build copies of themselves, and he planned to create tunneling devices that would multiply until they formed a perfect energy network throughout the asteroid field. During study groups, Jake listened to his classmates discuss their ideas with a mixture of awe and despair. They spoke of energy types that existed in parallel dimensions, machines that could think and evolve on their own, and materials that could exist in multiple states at the same time. Every solution seemed to require technologies that humanity would not develop for hundreds of years, if ever. Finn tried to help, explaining concepts in simpler terms when he could. His own project involved creating mathematical models that could predict energy flow patterns across 17 different dimensions simultaneously. When he showed Jake his preliminary calculations, the equations covered entire walls and used symbols that hurt to look at. "Do not worry so much," Finn told him one evening as they sat in their room. "Professor Veltar chose you for a reason. Humans were accepted into the Institute not because you are technologically advanced, but because you think differently." Jake appreciated the encouragement, but it did not make him feel better. Being chosen for thinking differently felt like being invited to a chess tournament because you were good at checkers. He spent his nights walking the empty corridors of the station, trying to clear his head. The Institute never truly slept. Students from worlds with different day cycles worked at all hours. He often passed laboratories where beings conducted experiments with equipment that defied explanation. Lights that existed without sources illuminated rooms where gravity seemed to work sideways. Machines hummed with energies that made his skin tingle. During one of these late-night walks, Jake found himself in an observation lounge with a perfect view of the asteroid field they were supposed to solve. The mining platforms looked like tiny stars scattered among the dark rocks. Power lines stretched between them like a spider web, but many of the connections flickered or went dark as he watched. Jake pulled out his notebook and began sketching what he saw. He drew the asteroids as simple circles and marked the platforms as squares. He tried to map the power lines, noting which ones seemed stable and which ones failed regularly. It was basic work, the kind of diagram a first-year engineering student might make, but it helped him organize his thoughts. As he stared at his simple drawing, something nagged at the back of his mind. The pattern of failures was not random. The power lines that failed most often were the ones stretched across the areas where the largest asteroids created gravitational interference. The stable connections were all in regions where the gravitational forces were more balanced. Jake opened his physics textbook and found the section on orbital mechanics. The math was basic, the kind of calculations he had done dozens of times in college. Force equals mass times acceleration. Gravitational force depends on mass and distance. Objects in space find stable points where gravitational forces balance out. He began doing simple calculations, working out the gravitational effects of the larger asteroids on the mining platforms. The math was straightforward, requiring nothing more than algebra and basic physics. But as he worked, a pattern began to emerge. The asteroid field was not chaotic at all. It followed predictable rules based on the gravitational interaction between the larger rocks. There were points in space where the gravitational forces balanced out, creating stable locations where objects could remain in position without constant adjustment. Jake had studied these points in college. They were called Lagrange points, named after an 18th-century mathematician. They were natural parking spots in space, places where the gravitational forces of multiple objects canceled each other out. He spent the next several nights in the observation lounge, mapping the asteroid field and calculating potential Lagrange points. His math was simple compared to what his classmates were doing, but it was also precise. He could predict exactly where stable positions would exist throughout the asteroid field. The more he worked, the more excited he became. What if the solution was not about fighting the gravitational anomalies with advanced technology? What if the answer was to work with the natural forces instead of against them? Jake began designing a power grid that used the Lagrange points as natural relay stations. Instead of trying to maintain power lines across unstable regions, the system would route energy through the gravitationally stable locations. The mining platforms could be repositioned to take advantage of these natural parking spots, and the power grid could follow paths where gravitational interference was minimal. His design looked embarrassingly simple compared to what his classmates were developing. There were no quantum fields, no dimensional manipulations, no exotic materials, just basic physics, conventional power cables, and careful positioning based on gravitational calculations that any spacefaring civilization could perform. But the more Jake worked on his calculations, the more convinced he became that his approach would work. The math was solid even if it was simple. The system would be stable, reliable, and could be built with materials and techniques available to any civilization that had achieved basic space flight. Jake began to realize that his so-called disadvantage might actually be an advantage. His classmates were so accustomed to using advanced technology that they automatically reached for complex solutions. They could manipulate quantum states and bend dimensional space, so that was what they tried to do even when simpler approaches might work better. Jake had no such advanced tools available to him. All he had was basic physics and simple math. But maybe that forced him to look at the problem differently, to find solutions that his more advanced classmates overlooked because they were too obvious. As the weeks passed and Jake refined his calculations, he grew more confident in his approach. His solution might not be impressive in terms of advanced technology, but it would work. It would be stable, cost-effective, and maintainable by any civilization in the galaxy. The question was whether Professor Veltar and his classmates would see elegant simplicity as sophisticated thinking or just as proof that Jake did not understand the complexity of the problem. In 3 more weeks, he would find out. Jake's breakthrough came during a particularly frustrating lecture on multidimensional energy matrices. Professor Veltar was explaining how advanced civilizations could route power through pocket dimensions to avoid physical interference, using mathematics that made Jake's head spin. As he listened to descriptions of reality anchors and dimensional stability fields, Jake found himself doodling in his notebook. He drew the asteroid field again, but this time he focused on the movement patterns. The asteroids were not just floating randomly in space. They orbited around each other in complex but predictable ways, creating a gravitational dance that followed the same basic laws of physics that govern planetary motion. That night, Jake returned to the observation lounge with his calculator and physics textbook. He spent hours watching the asteroids move, timing their rotations and mapping their gravitational relationships. What he discovered was beautiful in its simplicity. The asteroid field was essentially a miniature solar system with dozens of gravitational centers. Just like planets and moons created stable orbital points, the asteroids created zones of gravitational equilibrium throughout the field. These Lagrange points formed a 3-dimensional network of naturally stable locations, where objects could remain in position with minimal energy expenditure. Jake began calculating the exact positions of these stable points using equations he had learned in his second-year physics course. The math was straightforward. Gravitational force equals the gravitational constant times the product of 2 masses divided by the square of the distance between them. When multiple gravitational sources were involved, you simply added up all the forces acting on a point in space. For each potential Lagrange point, Jake calculated the gravitational forces from all nearby asteroids. Where these forces balanced out, he marked a stable position. The process was tedious but not difficult, requiring nothing more than patience and careful arithmetic. Within a week, Jake had mapped over 200 stable points throughout the asteroid field. They formed a natural network that connected every region where mining platforms were located. Better yet, the stable points were positioned in ways that would allow power cables to follow paths of minimal gravitational stress. Jake's solution began to take shape. Instead of fighting the gravitational anomalies with exotic technology, his system would use them as natural supports. Power relay stations positioned at Lagrange points would remain stable without requiring constant adjustment. Energy could flow through conventional cables along gravitationally neutral pathways, avoiding the stress that caused current systems to fail. The design resembled a spider web with the main power source at the center, and relay points positioned at calculated stable locations throughout the field. Each relay station would be a simple device, basically just a power transformer and signal booster that could be built with standard technology. The cables themselves would be conventional superconducting wires, nothing more advanced than what humanity already used for power transmission on Earth. Jake worked out the energy losses through his system and was amazed to discover they were actually lower than the quantum tunneling solutions his classmates were developing. Conventional cables might seem primitive compared to dimensional energy conduits, But they were also incredibly efficient when properly positioned and shielded. The positioning was the key insight that his classmates had missed. They were trying to overcome the gravitational anomalies instead of working with them. Jake's system turned the anomalies into advantages, using the natural stability of Lagrange points to create a power grid that would be more reliable than anything built with advanced technology. Jake spent another week refining his calculations and creating detailed blueprints. He used graph paper and pencils to draw his designs, occasionally checking his work with his basic calculator. His most sophisticated tool was a slide rule his grandfather had given him, an antique device that could perform complex calculations. Through mechanical precision, the simplicity of his approach began to worry him. While his classmates developed solutions that required materials costing millions of credits per kilogram and manufacturing techniques available to only the most advanced civilizations, Jake's system could be built by any species that had achieved basic space flight. The total cost would be a fraction of the alternatives, but was that a good thing or a sign that he was missing something important? Advanced problems were supposed to require advanced solutions, weren't they? Jake began to doubt himself, wondering if his approach was too simple to be taken seriously. He spent hours reviewing his calculations, looking for errors or oversights. The math checked out every time. His system would work, and it would work better than the alternatives in terms of reliability, maintainability, and cost. But it did not involve any cutting-edge technology or brilliant innovations that would impress his professors and classmates. Jake decided to test his theory by building a small-scale model. Using materials from the Institute's fabrication lab, he constructed a miniature version of his power grid. The model used tiny motors to simulate gravitational forces and LED lights to represent power flow. It was crude compared to the holographic simulations his classmates were creating, but it demonstrated his principles clearly. The model worked perfectly. Power flowed smoothly through the network even when Jake introduced simulated gravitational disturbances. The relay points remained stable, and the system automatically rerouted energy around any damaged connections. His simple spiderweb design proved to be remarkably robust and self-correcting. Finn watched Jake test his model and shook his head in amazement. "Your solution is so basic that it is brilliant," he said. "My people would never think to approach the problem this way because we would assume it was too simple to work." That comment gave Jake hope. Maybe his approach was not too simple, but rather elegant in its simplicity. The best solutions often were the ones that solved complex problems with straightforward methods. A wheel was simple, but it was also one of humanity's greatest inventions. Jake began preparing his presentation, knowing that he would need to explain his solution clearly to beings who thought in dimensions he could not imagine. He would have to convince them that sometimes the most advanced solution was the one that worked most effectively. Regardless of how sophisticated it appeared, his presentation materials were embarrassingly basic compared to what his classmates were preparing. He had hand-drawn diagrams, simple mathematical equations, and a crude physical model. No holographic projections, no quantum simulations, no reality-bending demonstrations. Just clear explanations of basic physics, principles, and how they could solve a complex engineering problem. As the presentation date approached, Jake grew more nervous but also more confident in his solution. He had found an answer that would work, that could be implemented immediately, and that would cost far less than any alternative. Whether his professors and classmates would appreciate the elegance of simplicity remained to be seen. The night before presentations were scheduled. To begin, Jake sat in the observation lounge one last time, looking out at the asteroid field that had inspired his solution. The mining platforms flickered in the darkness, their failing power connections a constant reminder of the problem that needed solving. Tomorrow, he would propose fixing those connections not with advanced technology that few civilizations could afford or maintain, but with basic physics and careful planning that any spacefaring species could implement. His solution might not win points for innovation, but it would solve the problem, and sometimes that was what mattered most. The presentation day arrived with Jake's stomach twisted in knots. He sat in the circular classroom watching his classmates set up their demonstrations, each one more spectacular than the last. Holographic displays filled the air with swirling galaxies of data. Machines that seemed to bend reality hummed with exotic energies. The very air crackled with advanced technologies that Jake could barely comprehend. Zara went first, her gaseous form shimmering as she explained her consciousness-linked energy network. Her presentation showed how thoughts could carry energy across vast distances, creating connections that existed in the realm of pure consciousness rather than physical space. The demonstration involved her mind directly controlling holographic energy flows, making power dance through the air with nothing but focused thought. Professor Veltar asked several questions about the stability of consciousness, bridges, and the energy requirements for maintaining mental connections across asteroid-sized distances. Zara answered with confidence, her glowing form pulsing with different colors as she explained concepts that made Jake feel like his brain was too small. Crix presented next, his forearms moving independently as he controlled multiple holographic displays at once. His self-replicating quantum tunneling devices would create microscopic wormholes between power sources and destinations. The devices would multiply and spread throughout the asteroid field like a living network, each one spawning copies of itself until every mining platform was connected through quantum tunnels. The demonstration was mesmerizing. Tiny points of light appeared in the air above the classroom, multiplying and connecting with threads of pure energy. Crix explained how the devices would mine raw materials from the asteroids themselves to build more copies, creating a self-sustaining network that would grow stronger over time. Other students presented solutions involving temporal energy loops that borrowed power from future versions of themselves, dimensional storage systems that kept energy in pocket universes until needed, and reality anchor points that could stabilize spacetime to prevent gravitational interference. Each presentation showcased technologies that seemed like magic to Jake. By the time his turn arrived, Jake felt like a primitive human about to show cave paintings to a group of master artists. His setup was painfully simple, a basic holographic projector displaying hand-drawn diagrams, a physical model made from scrap materials, and a slide rule that looked ancient compared to the quantum computers his classmates used. Jake walked to the center of the classroom and looked around at his audience. Beings of crystalline energy, living gas clouds, metal-skinned entities with too many limbs, and creatures that existed partially in other dimensions all waited to see what the primitive human had managed to come up with. My solution uses basic physics, Jake began, his voice sounding small in the large room. Instead of fighting the gravitational anomalies in the asteroid field, I propose working with them. He activated his holographic display, showing his hand-drawn map of the asteroid field. The diagram looked childish compared to the sophisticated visualizations his classmates had created, but it clearly showed the positions of mining platforms and the gravitational relationships between asteroids. Gravitational forces in the asteroid field follow predictable patterns. Jake continued, gaining confidence as he explained familiar concepts. These forces create natural equilibrium points, called Lagrange points, where objects can remain stable with minimal energy input. Jake walked through his calculations, showing how basic orbital mechanics could predict the location of stable points throughout the asteroid field. He used simple equations that any first-year physics student would recognize. Force equals mass times acceleration. Gravitational force varies with mass and distance. Objects in orbit follow elliptical paths that can be calculated with basic mathematics. Murmurs rippled through the classroom. Some students seemed confused by the simplicity of his approach. Others appeared intrigued by the elegance of using natural forces instead of overriding them with technology. Jake demonstrated his physical model, showing how power could flow through a network positioned at gravitationally stable points. The crude device with its tiny lights and simple motors looked like a toy compared to the reality-bending demonstrations his classmates had presented, but it clearly illustrated his principles. The system requires no exotic materials or advanced manufacturing techniques, Jake explained. It can be built and maintained by any civilization that has achieved basic spaceflight. The energy losses through conventional cables are actually lower than quantum tunneling solutions because there is no dimensional interference to account for. Jake showed his cost calculations, comparing his system to the alternatives his classmates had proposed. His solution would cost less than 1% of the quantum tunneling network and could be implemented immediately using existing technology. Maintenance would be simple enough that mining crews could handle repairs themselves without requiring specialists in exotic physics. When Jake finished his presentation, the classroom fell silent. The quiet stretched uncomfortably as Professor Veltar's crystalline form pulsed with unreadable energy patterns. Jake began to worry that his simple approach had been too primitive to take seriously. Finally, Crix raised one of his forearms. "But where is the advanced technology?" he asked, his metallic voice echoing in the chamber. "How does this demonstrate mastery of theoretical applications? This is just basic physics that any student could understand." Jake took a deep breath, realizing this was the moment that would determine whether his approach was seen as elegant or inadequate. Sometimes the most advanced solution is the one that solves the problem most efficiently, he said, surprising himself with the confidence in his voice. Advanced technology is wonderful, but it should be used when it is needed, not just because it exists. This problem does not require quantum manipulation or dimensional engineering. It requires understanding the natural forces already present in the system and working with them instead of against them. Jake gestured to his simple model. "My solution might not showcase cutting-edge technology, but it will work reliably for centuries without requiring exotic materials or specialist maintenance. It can be understood by engineers throughout the galaxy, implemented quickly, and scaled to any size network." More silence followed as Professor Veltar continued to pulse. With shifting colors, Jake began to panic, wondering if he had just argued himself into failure by admitting his solution was too simple. Then another student spoke up, a being that looked like living mercury. "The human raises an interesting point. Our solutions are impressive, but they all require resources and expertise that most civilizations do not possess. His approach could be implemented by anyone." But surely complexity indicates sophistication," another student protested. "If the solution is too simple, how can it be considered advanced?" Jake realized that the debate was no longer about his presentation specifically, but about the fundamental question of what constituted advanced thinking. Were the most sophisticated solutions necessarily the most complex ones? Or could true sophistication lie in finding simple answers to complex problems? Professor Veltar's form began to pulse more rapidly, and Jake sensed that the crystalline being was about to deliver a judgment that would determine not just his grade, but his entire future at the Institute. The moment stretched endlessly as Jake waited to learn whether his simple human approach had any value in a galaxy full of beings who could manipulate the fundamental forces of reality. Professor Veltar's crystalline form suddenly blazed with brilliant white light, startling everyone in the classroom. Jake had learned that this pattern indicated deep admiration among the professor's species, but seeing it directed at his simple presentation felt surreal. "In 3,000 years of teaching," Professor Veltar said, their voice resonating through the chamber with unusual intensity, "I have never witnessed a solution that demonstrates such profound understanding of fundamental principles." The classroom erupted in surprised murmurs. Jake felt his legs go weak as the professor continued. "Student Morrison has achieved something remarkable. His solution is not just correct, it is optimal." Professor Veltar gestured, and Jake's crude diagrams were replaced by sophisticated computer simulations. "I have run comprehensive analyses of all proposed solutions. The human's basic physics approach outperforms every advanced technology solution in reliability, efficiency, and practical implementation." The simulations showed Jake's power grid operating flawlessly under various stress conditions. When gravitational anomalies disrupted other systems, his network automatically rerouted power through alternative Lagrange points. When individual components failed, the system continued operating with minimal degradation. Most importantly, the simulation showed his solution working perfectly for over 500 years without requiring major maintenance. But how is this possible? Zara asked, her gaseous form flickering with confusion. Surely advanced technology must produce superior results? Professor Veltar's form pulsed with what Jake now recognized as amusement. This question reveals the fundamental flaw in how most advanced civilizations approach problems. When you possess quantum manipulators and dimensional shifters, you tend to use them even when they are unnecessary. Advanced technology becomes a hammer that makes every problem look like a nail. The professor moved to the center of the room, their crystalline body casting rainbow patterns on the walls. Student Morrison's human perspective provided a crucial advantage. Coming from a civilization that still struggles with basic engineering challenges, he was forced to examine the problem without assuming that complex solutions are inherently superior. Jake listened in amazement as Professor Veltar explained how his supposedly primitive background had actually been an asset. Humans have not yet developed the technological sophistication that can blind more advanced species to simple solutions. Mr. Morrison saw what others missed because he was not distracted by the possibility of using exotic technologies. Crix raised two of his forearms in a gesture Jake had learned indicated serious interest. Are you saying that being less technologically advanced can sometimes be an advantage? Precisely, Professor Veltar replied. Advanced civilizations often forget that the purpose of technology is to solve problems, not to demonstrate sophistication. The best solution is always the one that solves the problem most effectively, regardless of how impressive it appears. The professor activated another simulation showing the cost comparisons Jake had calculated. Student Morrison's system can be implemented for less than 1% of the cost of the quantum tunneling alternatives. More importantly, it can be built, operated, and maintained by any civilization that has achieved basic spaceflight. This makes it truly practical for galaxy-wide implementation. Jake felt overwhelmed as he realized the implications of what Professor Veltar was saying. His solution was not just academically successful, it was actually going to be used in the real world. The Outer Rim mining colonies have agreed to implement Mr. Morrison's design as a pilot program, the professor announced. If successful, his approach will become the standard for power distribution in gravitationally complex environments throughout the galaxy. The classroom buzzed with excited conversation as students processed this information. Jake stood in the center of it all, still hardly believing what was happening. 3 months ago, he had been a struggling college student who felt completely out of place among galactic geniuses. Now his simple physics solution was being adopted by civilizations across the galaxy. Professor Veltar approached Jake, their crystalline form glowing with warm approval. You have taught us something important today, Mr. Morrison. You have reminded us that wisdom sometimes lies not in knowing the most advanced techniques, but in understanding when simple approaches are superior. Over the following weeks, Jake found himself at the center of a minor revolution in how problems were taught at the Institute. Professor Veltar introduced a new concept called applied simplicity, encouraging students to examine whether basic approaches might work before reaching for exotic technologies. Other professors began incorporating similar principles into their courses. Students started learning to analyze problems from multiple perspectives, including the viewpoint of less technologically advanced civilizations. The Institute's library created a new section dedicated to primitive, problem-solving techniques from worlds throughout the galaxy. Jake received offers from research institutions on dozens of worlds, all wanting to study human approaches to engineering and problem-solving. The galaxy had suddenly become very interested in how a species that had barely achieved faster than light travel could find solutions that eluded much more advanced civilizations. But the most satisfying moment came when Jake received a message from the Outer Rim colonies. The pilot implementation of his power grid had exceeded all expectations. The system had operated flawlessly for 6 months without a single failure. Mining output had increased by 30% because platforms no longer lost power during gravitational anomalies. The message included a request that surprised Jake even more than his academic success. The colonies wanted him to help design similar systems for other challenging environments throughout the galaxy. They offered him a position as chief engineer for Simple Solutions, a newly created department dedicated to finding basic approaches to complex problems. Jake accepted the position but also chose to remain at the institute as a part-time instructor. He began developing a new curriculum called Fundamental Problem Solving, teaching students to look for simple solutions before attempting complex ones. The course became one of the most popular offerings at the institute, attended by beings from the most advanced civilizations in the galaxy. In his first semester as an instructor, Jake taught students to question whether their problems actually required the sophisticated solutions they instinctively reached for. He showed them how to break complex challenges down into basic components, apply fundamental principles, and build up from simple foundations rather than starting with advanced techniques. The approach proved remarkably effective. Students began solving problems with elegant simplicity that impressed their other professors. More importantly, their solutions often worked better than the complex alternatives they might have developed using advanced technology. Jake's favorite moment as a teacher came when a student from one of the galaxy's most technologically advanced civilizations presented a solution to a complex logistics problem using nothing but basic mathematics and careful observation. The student explained that they had learned to see the problem through human eyes, looking for simple patterns rather than assuming complexity was required. On quiet evenings, Jake still visited the observation lounge where he had first worked out his asteroid field solution. He would look out at the stars and think about how far he had traveled, not just physically but intellectually. He had come to the institute feeling primitive and inadequate, only to discover that sometimes being primitive was exactly what was needed. The galaxy was full of beings who could manipulate quantum fields and bend spacetime to their will. But it had needed a human with a slide rule and a basic physics textbook to remind everyone that the best solutions did not have to be complicated. Sometimes the most advanced thing you could do was to keep things simple. Jake had learned that humanity's greatest contribution to the galaxy might not be advanced technology, but rather the ability to step back from complex problems and ask whether there might be a simpler way. In a universe full of beings who had forgotten how to think simply, that was a perspective worth more than all the exotic technologies in the galaxy.